Hey everyone, welcome back to Bayesian statistics. Last few times, really for the beginning of this semester, we were talking a lot of general terms. So last time I talked about the different shapes of priors. I defined things like the likelihood and the prior distribution. And I even threw up some different named priors like uniform 0, 1, beta 1, 1, beta 1/2, 1/2, normal something, something else. So we're going to start to get a little bit more specific. And to be specific, we need to get a little bit more mathematical. So a bit of a calculus alert. I think that this particular set of 2 videos, for those with a strong mathematical background, I bet I will frustrate you with how slowly I'm going. For those with a little bit less of a mathematical background, maybe you took calculus a while ago, I might frustrate you with how much mathematics is involved in the next few lectures. So if I succeed with that, I think I will be kind of picking that middle path, frustrating all the students. That is in meaningful ways. That is where I'm going for the next couple of lectures. Okay, with that, we're talking about Bayesian ingredients. And in Bayesian statistics, we have the likelihood, the prior, and the posterior. So the likelihood is a key component of any posterior analysis. You know, frequentist analysis, it is everything. The likelihood is everything. So let me start to sort of demonstrate how we derive and work with a likelihood. So we say that this is a very common assumption that is made. It's called the i.i.d. assumption. Whether or not it is formally stated, it is almost always made. So what we're saying is we have n observations, and each because we have a subscript I, each of our n observations is assumed to be independently and identically distributed, and this is what this tilde means, according to some distribution, which is governed by our parameter theta. And in notation, this is what we would write. Our data set, our n observations, are distributed, tilde is read as distributed as, according to some distribution with some, governed by some parameter. Notice that if we have a normal distribution, we actually have a vector of parameters, right? Because a normal distribution has a mean and a standard deviation or variance. But let me be very clear about exactly what this means. So what this means is the likelihood of all n observations what you're thinking about, and I forgot to condition it on our parameter, given some parameter, you're thinking of an intersection of our first observation, second observation, and third observation, and under independence, which is one of the i's, right? Under independence, which is our first I, we can write the following. It's the likelihood of the first observation times the likelihood of the second observation times so on and so forth until we reach the last observation. So without assuming the independence, without assuming that conditional on our parameter, our observations are actually mutually independent. That's the first I of i.i.d. We could not take the product. Why the product? If you recall to go back to your intro to stats class, and we said, if events A and B are independent, then the intersection of A and B can be written as the probability of A times the probability of B. So here we have the intersection of n observations given some parameter, and we're basically writing out the likelihood of the first observation times the likelihood of the second observation times all the way until we get to the likelihood of the nth observation. Now, notice that I am changing the observations. The observations are different, but the parameter that I'm using in there is completely identical. So, identical, because I'm assuming all n observations came from the same distribution. Let me repeat. The only reason I'm allowed to reuse this parameter is I'm assuming that all n of my observations came from an identical distribution. So, all n observations came from a distribution, I'll say, governed by theta, the same theta. That would not be the case. If this were not the case, I would have to write something like theta 1, theta 2, theta 3. But then the question is, how much information do I have about each individual theta? We want a lot of information to estimate just one parameter. In fact, a rule of thumb out there is that you want at least 30 to 50 observations per parameter you're trying to estimate. That's a rule of thumb. Clearly, that rule of thumb has to be modified for a lot of different reasons. But this would be a terrible, the way I have it written right now, where the first observation is governed by a unique distribution, and the second observation is governed by a unique distribution, and a third observation is governed by a unique distribution. You don't have enough information to make any reliable estimates. And so the only way for us to estimate a singular theta, I erased too much there, I will replace it, is to assume that our data were identically and independently distributed, or independently and identically distributed, and so all n observations came from a distribution governed by a common theta. Okay, so this is what is assumed. That's a lot that is assumed by the i.i.d. assumption, but that allows us to evaluate an n-dimensional likelihood. N-dimensional likelihood. We have to make some simplifying assumptions for that. All right. So a simple example, suppose that we have a coin. It's not just any coin. Let's leave something to the imagination. It's a special coin. It's the Susan B. Anthony $1. And I flipped it 3 times. Do I have a Susan B. Anthony dollar? I do not. I used random.org to flip the Susan B. Anthony dollar. I flipped it 3 times. I observed 2 heads. My parameter of interest is theta, which is the probability that a coin produces a head. So my Y1 is maybe a head or 1. My Y2 is also a head. And my Y3 is maybe a tail. I hear some of you screaming at me, well, couldn't the second 2 be heads? Couldn't the middle one be the tail? But if we assume i.i.d, it doesn't matter in which order we perform this multiplication, right? So sometimes this is called exchangeability. That is, we can exchange which observation is where. If the independence assumption is violated, then the exchangeability does not hold. then we need to keep track of which observations go together. Maybe they're observations that were collected close to one another in space or time. Maybe they're observations that were collected on the same subject. But under i.i.d, our observations are exchangeable. That is, it doesn't matter in what order I record my data. The resultant likelihood is the same. So if we're going to build our likelihood one at a time, right, we define each observation as a 1 if it's a head and a 0 if it's a tail. And then here I'm building the likelihood for all three. Under i.i.d, here is the likelihood of my first observation, by the way. Each likelihood, each flip is a Bernoulli, which is just a distribution of a binary outcome where there is some probability of a 1 and some probability of a 0. So each flip can either be a head or a tail. That's a binary outcome. And there is some probability of it being a head and some probability of it being a tail. So that is a classic Bernoulli distribution. If you look up the Bernoulli distribution on Wikipedia, this is my Bernoulli distribution. You will notice that there is a lot of different ways of writing the Bernoulli distribution, but if you follow where my cursor is, here is my distribution function for the Bernoulli. Notice that Wikipedia just uses p's where we use thetas, and the Wikipedia uses k's where I use y's. But the form of the Bernoulli is the same. Right? We have our probability of a success, probability of a head, probability of a 1. For some reason I'm missing it. No, it does not want to help me. That's okay. The probability of the first observation being a head to the power of whether or not it was a head. Here is the probability that the first flip was tails to the power of whether or not the first flip was tails. And because we are independently and identically distributed, it's the same theta. I, in the end, did flip the same coin. If for some reason I got a different coin on my third flip, then I could not use theta. Then this theta could not be used. I would need to use something like theta star because I would change coins. We're not changing coins. We are identically and independently distributed. So I get to build my likelihood just like that. In terms of mathematical notation, let's see if now my erase function works, and it does. Mathematicians like to be nice and efficient, and so this is just a product. This is a product from I equals 1 to 3, which by the way is just n. Each flip is again a Bernoulli theta. All right. So the exact form, the exact numerical form would depend on whether or not, how these y's came out to be either 1s or 0s. All right. So moving on. There's a bit of notational trickery because in the frequentist analysis, theta is very much considered an unknown fixed term. And however, when we start to work with the log likelihood, the notation is like this. We have the script L of theta given y, which gives us an illusion that theta is changing, which is all very, very weird because again, in a frequentist analysis, theta is very much a fixed constant. So don't be too confused about the notation. It's the technicalities of the notation is not something I would like to focus on in this particular class. But if you're going to take mathematical statistics, their notation will be maybe far more important. So just maybe quickly, here is the distribution of y given a certain parameter, our likelihood. This clearly states that theta, because it's given, it's a constant, but once we take the natural log, this is now going to be written like this, which is the natural log of our likelihood function. So speaking of the natural log of our likelihood, let's review why we heart natural logs. Natural logs help us deal with complicated expressions. They break down multiplication into addition, and natural logs are numerically more stable. And so things like R work better when you're dealing with log likelihoods than regular likelihoods. If you're trying to work with pencil and paper, you would much rather be adding stuff together than multiplying stuff together. It's a lot easier to track, it's a lot easier to work with, it's a lot easier to differentiate, and it's a lot easier to integrate. So, recognize from a few slides ago that this is our likelihood of flipping our coin 3 times, right? It's a product, and on each flip, we have a Bernoulli. But I want to derive the log likelihood. So I'm gonna go ahead and go to my next slide and do this nice and slow. So the log of theta given y1, y2, and y3, I did have 3 flips, is the natural log of my product. All right, and that is, again, just nothing more than a Bernoulli distribution. The log of a product is the sum of the logs. The log of a product is the sum of the logs. The log of a product is the sum of the individual logs. I always want to take and apply this the opposite way, but you can't. The log of a sum is nothing. But the log of a product, you can just break out as summing the individual logs. So what this means is, in mathematical notation, it's the sum, and I'll be using 3 here, although technically that's n up there, of the individual logs. So I actually want to go back and work out this product a little bit more slowly. This is exactly where folks with a lot of math background are going to be upset with me, but still. Okay, I'm taking, when I'm working with this expression up top, I'm taking the natural log on the outside of theta to the power of y1, theta to the power of y2, theta to the power of y3 times, and there's a multiplication sign in between each one, right? All right, 1 minus theta to the power of 1 minus y1, 1 minus theta to the power of 1 minus y2, 1 minus theta to the power of 1 minus y3. So if you remember how this kind of expression works, the powers of the same thing add together, right? The powers of the same thing add together. So what I can do is keep the log on the outside, and this actually becomes theta, y to the power of all of my y's added together. And this becomes my 1 minus theta to all of these powers added together. And we have to kind of keep track of the minuses. Okay, guys, you got to keep track of the minuses. Doing the best I can with this stylus. All right. It's a good thing we have a sample size of only 3. Otherwise, we'd be here all day. Good thing we have computers. Okay. So now I'm going to be a little bit more efficient. Again, the log is just the whole expression. Be a little bit more efficient. This is just the sum of my y's. All right, sum of my y's. This is the sum of 1 minus y. But I'm going to have n ones minus 3 y's, a sum of 3 y's. So what I'm going to actually write there is, in this case, for my example with an n of 3, this is just 3 minus the sum of y's. Now recognize this way. This is the total number of successes I observed out of however many trials. And this is the total number of failures I've observed out of this many trials. For a coin flip, this is how many heads I got. I have 2 heads. And this is how many tails I got. 3 minus 2 is 1 tail. So now I can more easily, I will actually just go ahead and add a slide at this point. I can more easily take the log of that expression. All right, so I'm going to take the log of that expression, and remember that there's a multiplication sign right there. So log of a product is the sum of individual logs. So I'm going to do log theta sum y plus log theta of this. Okay, cool. Go back to why we love our natural logs. Flip up to slide 14. All right, I use this. Now what? Now what's going to help me? Oh, I have a natural log of something to a power, right? So I get to bring the power down. I'm over here and I get to bring the power down. So this is the sum of y's log theta plus, I have it here as n. It's just the force I have it. I intended to keep it as 3. Apologize for that. But it's really n, but in this case, n is 3. So I just want to keep it as 3. Throw a constant in there. All right, and now, and I made another typo, didn't I? I made another typo. Because this is the probability of a head raised to the power of how many heads I have. This is the probability of a tail raised to the how many tails I have. So I didn't copy it over correctly. This expression over here was supposed to be 1 minus theta raised to this power. Okay. Log 1 minus theta. And I'll repeat because I try all the time. I'm like, I can do something with this expression. You cannot. The log of a multiplication can be expressed as a sum of logs. The log of 1 minus theta is what it is. So here is our expression for the log likelihood for my 3 coin flips. Okay. So all of that was supposed to go right there. If we were in person, I would do this on the board. So one more thing to do before we end this particular video. Frequentists. our second favorite people. I'm playing. Frequentists. The way they would make an estimate is they're going to maximize, they're going to call it a maximum likelihood estimate. They're going to maximize the log likelihood. They're going to maximize this expression with respect to the parameter. They're going to maximize this expression with respect to the parameter. And that value will be called the maximum likelihood estimate. How? What we're going to do is we're going to take the first derivative, calculus alert. Set equal to 0 and solve. All right. So here we go. If you're awesome at derivatives, then feel free to skip ahead because I'm going to do this slowly. I'm not that good at math. I got to go slow. So here's my expression. I need to take the derivative of this quantity with respect to theta, and then I'm going to set that expression equal to 0. I'm going to do this in two parts because the derivative of this expression is the derivative of this plus the derivative of this. So we're going to do the derivative with respect to theta. Of this quantity plus the derivative with respect to theta of this quantity. Okay. This first one's pretty easy. This first one's pretty easy if you remember how the derivative of a natural log works. So this sum of y's is constant with respect to the parameter, so it just comes out. And then we take the derivative of log theta, and we get 1 over theta. Cool. That's good. Yes, this multiplier is constant with respect to theta, so it comes out. But now, to take the derivative with respect to theta of this function, it's a little bit more complex. We have to use the chain rule. And so we take essentially we apply the derivative of the log to the outside. And now we take d theta of the inside. By the way, we implicitly did the same thing here, but when here was d theta of theta, which is equal to 1. Here, d theta of this quantity, d theta of 1 is 0. d theta of negative theta is negative 1. So we have to really keep track of the negatives, right? We have a negative 1 times this times that. So I'm going to go ahead and update, erase this to clean it up. This minus sign updates my this sign. All right. So my goal, take a step back. I'm being a frequentist right now. I'm going to maximize my log likelihood with respect to my parameter. And I'm going to take that value, which maximizes the log likelihood, and call it my frequentist estimate or maximum likelihood estimate. I've taken the first derivative. And actually, this function on the bottom is called the score function. Right? It's a function of your data and theta, and it's called the score function. So I need to add another slide. All right. So let me grab, okay. So here is my first derivative. I'm going to write it out, and I'm going to set it equal to 0, because it is when the first derivative is equal to 0 that I obtain my maximum. Yes, I know you're supposed to check the second derivatives too, but I'm not going to do that right now. Remember where that negative sign came from. When you're doing this by hand, being off by a sign can really break everything. All right, so when I was taught to do this, back in the olden age, when we set this equal to 0, we put the hats on. So when we say we put the hats on, we replaced theta with its estimate, which is theta hat. When we set it equal to 0, we replace theta with this estimate, theta hat. Now we solve for theta hat, the maximum likelihood estimate of theta. So first things first, rearrange a bit. I know you're about to see me do arithmetic. It's very exciting, but it's good practice. It's good practice. It's attention to detail. When in doubt, we should all do arithmetic at least once a year. I'm playing around. Okay, we added the second expression to both sides, so we get this. Now we're going to cross multiply. I'm going to cross multiply, right? We're trying to isolate theta hat. So when I cross multiply, I have sum of y's times 1 minus theta hat on this side. And I have 3 minus sum of y's times theta hat on this side. Or I distribute. I get sum of y's minus sum of y's times theta hat equals, distribute this, I get 3 theta hat minus sum of y's theta hat. And you know what? I love it when this happens. Love it when this happens, because I have the same thing on this side as I do on this side. That means we can add that quantity to both sides and cross it out. We're here. I need to solve for theta hat. That will be my maximum likelihood estimate. So that means my theta hat MLE is, this is super exciting. Yeah, there it is. Sum of y's over 3. Recognize this is nothing more than the sample average. Sample average. All right. Very cool. So, come back to this slide. Nope, that's the wrong slide. We just completed this task. We have derived the log likelihood by recognizing how the i.i.d assumption works and then taking the natural log of that quantity. And we went back deep into our calculus knowledge to take the first derivative of the log likelihood with respect to theta. We set it equal to 0, and we put the hats on, and then we solved for theta hat. We have obtained, oh, it's not p, it's theta. We've obtained just a single point estimate of theta that maximizes our log likelihood, that maximizes the chances of observing our exact data set. So how would the Bayesians do it? Stay tuned for the next video when we're going to work with the Bayes theorem. So I will end this recording and I'll pick it up in a few minutes.